Okay, I'm going to try to quickly do a review of electrophilic aromatic substitution when there's already a substituent on the ring for my students. This is really late. They have their exam pretty soon, but I wanted to just try. So sorry that it took so long. But okay, let's go over the basics of electrophilic aromatic substitution. Essentially, this double bond will attack. The benzene will lose its aromaticity and attack a really positive electrophile. And then when it adds on, it gets a positive charge. And that positive charge is stabilized by resonance through the ring. So the positive charge can move here and it can move here. So that stabilizes a positive charge. Now, there's nothing on the benzene ring to start with. It doesn't really matter where the electrophile adds because it's all the same through symmetry, and the ring will be stabilized the same. But if your benzene is already substituted, it can add either, so if we already have a group right here, it can add either ortho, meta, or para to the group. And I'm going to start with what happens when it donates or when the electrophile adds ortho to your already existing group. You get your group is right here. Your electrophile is added right here, and it was the electrons in this bond that left. So there's a positive charge, just like there was before, right here. But in this case, the positive charge, it'll be stabilized around the ring, just like we saw up here. But if you have an electron donating group that is there that can add electrons, there will be an additional resonance structure, which makes it more stable because the electron donating group would be positive with your electrophile down here. So that's one extra resonance structure. So they all have 3 resonance structures, but this is an extra resonance structure. So if you have a group on your molecule that has electrons on it, it typically is an ortho-para director, because if the molecule adds at the ortho position, the carbocation is right here, and these electrons will be able to make an additional resonance structure and stabilize things added at the ortho position. It does the same thing for things stabilized at the, sorry, I'm going to zoom out a little so you can get the whole picture here. It does the same things for if you add at the para position. If you have your group at the para position, and let's see, your electrophile would add right here, and you would get, your group is here, and if your electrophile adds ortho, then the double bond right here is the one that broke, this one right here. So your positive charge goes there, and so through resonance, your structure will be able to move the positive charge here. And then if you have your electron donating group and there's a lone pair, it can do that additional structure right here. So either the ortho or the para position will be favored by donating groups or groups that have lone pairs on them. Now, you can imagine if this was, instead of donating electron withdrawing, the positive charge being right next to the electron withdrawing group would be not good. So instead, if you have electron withdrawing group, the substitution is favored at the meta position. So if you're to imagine you have your donating group here, and it's at the, your substitution occurs at this meta position, you would get your group still here with this, your electrophile added at the meta position, and your positive charge left behind right here. So the resonance structures for this would never actually end up on the donating group or withdrawing group if you add at the meta position. So because of that, if something was withdrawing and taking electrons away, the positive charge would never want to end up right there. So electron withdrawing groups would favor the meta position. They want to substitute right there because the positive charge never has to end up on the donating group. But electron donating groups want to go to the ortho or para position because the positive charge does end up right there on the donating group. And if the positive charge ends up right there on the donating group and there's lone pairs on our donating group, we can have an additional resonance structure. That's only if it has lone pairs. The other way is through induction. So if the group that you have is less electronegative or the same electronegativity, like CH3, it can add electron density to stabilize a positive charge right there, just as how a tertiary is more stable than a primary carbocation through induction as well. Or if you have something that's really electron withdrawing, like fluorine is electron withdrawing because it's very electronegative, which is why it deactivates the ring. But because it has that lone pair, it can still go into resonance. So I feel like that's not the best explanation, but I'm really pressed for time. So all that to say that if you have groups that have lone pairs, they are typically going to be electron donating groups that favor ortho-para substitution by resonance. Or if you have methyl groups, or I think that's the base one I can think of right now, that adds electron donation via induction. Or you could have electron withdrawing groups like if you had 3 fluorines off of a methyl, that would be withdrawing via induction. Or nitro has a positive charge right here. So the nitro group looks like this. So if there's a positive next to it, it could not go through resonance. In fact, it's much more stabilized without the positive charge. So this could be withdrawing by resonance or induction. And then, so either of those, because nitrogen is also more electronegative. Another group is like an acyl group because that's partially positive right there. So it's by induction pulling the electron density towards itself. But one that we had on a quiz that stumped a lot of my students is I had a benzene ring with an oxygen here and a carbonyl. And I think because they saw the carbonyl, they thought, oh, that's electron withdrawing because it's partially positive. I've learned that carbonyl groups are electron withdrawing, but because of the ability for resonance here to stabilize a positive charge, this actually would be donating by resonance because of these lone pairs that would add electron density. So that's a very quick overview of ortho-para versus meta directing effects for aromatic rings. It's not comprehensive. I'd like to make a more in-depth one, but this is all I have time for today, and my students' exam is soon, so I just wanted to give them the opportunity to check that out. Okay. Hope that was helpful. Good luck on your exam.